My name is Rolf Gersonde. I work for the City of Seattle in Seattle's mountain watersheds for Seattle Public Utilities. And we are managing about 100,000 acres primarily for drinking water supply, as well as for habitat under a habitat conservation plan. And I guess if you're looking for bias, look no further. This is about water, drinking water in particular. So my task here is hydrology. As I like to say for the after lunch speaker, I'll try to put you to sleep gently and make you feel like you learned something new on the side. So forest hydrology and climate adaptation. So what I'll try to do here is go through some background on hydrology and hopefully lay some groundwork for understanding how forests interact with precipitation and runoff, so that you can get an idea for how would you manage or change management in order to manage for continued or improved hydrology or runoff from the forest. So to start with that, I want to say that runoff and drinking water are not the only objectives one can have when thinking about forest hydrology. There are others. There are such things as stream habitat, of course, fish habitat. They're all influenced by how the forest interacts with the incoming precipitation and the runoff. And of course, there are also objectives relating to tree water status. So forest health is a big one. Trees that are well hydrated are likely to be more resistant to insects and pathogens. And then, of course, forest productivity. Our iconic Northwest forest is known for its productivity, but that's pretty much because of the precipitation we get here, because of the hydrology. And so productivity not only is not only important for forest product industry, but also for habitat creation, because many of the habitat elements that we're interested in are a product of great productivity. Large trees, deep crowns, deep canopy and so forth. So that said, we can easily see that all of these objectives are affected by future climate change. Maybe not so much by total change in precipitation, but as Jessica mentioned earlier, at least by the timing of the runoff. When the runoff occurs, that we expect a difference in future runoff than we have today. I borrowed this slide here from her. You see in the black line, this is a runoff pattern, stream flow from a watershed that has some higher elevation snow integrated in it. And the expectation is that it, over time, moves from black to blue to green to red, sort of a push in the peak of the distribution of runoff more towards the winter and not so much into the spring. A lack of snowmelt, maybe, but also different precipitation patterns, and then an extended summer low precipitation or low runoff period. Right from the get-go, pay attention to some of these graphs are hydrology graphs, and they live in a different universe. They start in October and end September, so that's the water year for hydrologists. And some of the graphs are going to be hydrology graphs, and some of them are calendar graphs. So what I'll be talking about is in particular two different forms of runoff. We differentiate here in particular peak flows and base flows events. The peak flow events here, these spikes, the dark blue spikes, are associated with storm events, with rain events that occur over the winter in particular. And then the lighter blue here is the base flow hydrograph, which is the contribution of the groundwater flow into the streams. So that happens all year round. But you see here in the summer months, July, August, September, and over there in October, there's a big proportion of the stream flow is only contributed through base flow. So it becomes important to us to manage both the peak flows and the base flows in some ways if we want to understand hydrology and hydrological management into the future. So let's start off with talking about regulating runoff. This has been a big issue over probably the past 70 to 80 years. The discussion about how can we maximize runoff from forested watersheds overall, whether we harvest them and clear the land to increase the runoff, or do we keep some forest alive? Is there a happy medium? Has been a long-standing discussion, and I want to go through a few things here: watershed yield, peak flow, and hydrologic regeneration, to lay out to you what the discussions used to be and what we ended up nowadays thinking about forest hydrology and total runoff from watersheds. So what people looked at over the past 100 years maybe were different studies that looked at land clearing, forest clearing, and the effects before and after of runoff. And this graph put together here looks at many different studies and shows if you clear the canopy cover from 100 to 0%, you get an increase in stream flow. So that would indicate the more land we clear, the more runoff we get. But at the same time, people also started looking at peak flow events. Those were the spikes I showed you on the graph. With increased clearing or removing of forest cover, people noticed that those peak flow events increase as well. So increased scour in streams occurred, increased sedimentation events occurred, and changed habitat in streams and water quality as well. So those two together give us a first indication that there's got to be somewhere a happy medium where you don't increase peak flows and get some runoff from the forest as well. Most of these studies also were conducted sort of as a before and after comparison. So you have a forest, and then you clear the land and you measure before and after what the runoff differences are. What we've noticed overall is that our classic vegetation pattern in the Pacific Northwest is that we have a rapid vegetation regrowth after a clearing, right? So much of the signal that we've seen from increased runoff after land clearing quickly changes because the forest grows back tremendously fast. In our area, probably some of the most productive forest in North America, we see this happening in a few decades. And these long-term studies where people compared watersheds, some that were cleared and some that they were not cleared, really give us an appreciation now how that works out over the long term when we clear lands. So here's a little bit of a wiggly graph, but it's a recent study that has come out just 3 years ago. And it compares different watersheds. So they looked at watersheds here in Western Oregon. Some of them were cleared and some of them were not cleared, and compared the runoff patterns. Over there at year 0 on the horizontal axis is the time when some of the watersheds were cleared, and then the lines show you the differences between the cleared and non-cleared watersheds. And when the values are positive below 0, that means that the cleared watershed had more runoff. When they're negative, it means that the not cleared watershed had more runoff. So you see there's a period here, maybe over 10 to 20 years, when the cleared watersheds certainly had more runoff, in particular during the summer. This is July to September runoff. But then after that period, we find this amazing pattern where the cleared watersheds that are now growing back very densely as a young forest start to have lower runoff. And this is the first time where we see this pattern. We haven't seen these long-term studies ever before. So we are now at maybe year 40, 35 to 40 for some of these cleared watersheds, and we see still less runoff from the cleared watersheds that have grown back densely. Overall, our expectation is that recovers at some point, that the hydrologic recovery regulation recovers over time, but that may not happen before age 80 or 100. So this is sort of where we stand today on land clearing for maximizing runoff. Important to know when we want to manage runoff in the future, when we have different patterns, to understand what does the forest structure do and how does it interact with runoff from forests. So, managing base flows. I'm coming back to that to look at the hydrologic effects, particularly on stand age and structure. So what do we derive now from these studies, and how do we look at that today? Here is some data from a study also in Western Oregon by George and Moore, looking at two different stands, one 40-year-old and one 450-year-old. And somebody asked that question earlier today, what is it about old trees? Do they have a different hydrology than the younger trees? And she could clearly show by looking at transpiration how much water basically gets transported through the stem, from the roots to the stem, and transpires through the leaves, and showing that the 40-year-old tree could transpire up to 3.5 times more water than the old forest, which is an amazing piece of work that has sat there for maybe 10 years before somebody picked it up again. So the difference is the old forest does seem to transpire less water than the younger forest, which is more productive. This work was picked up by a research group from the EPA. Bob McCain was the principal investigator here. They used this information about the effect of stand age or tree age on hydrology and transpiration, and put that into a hydrologic model. Basically a model that looks at the forest cover on the landscape and models the runoff, compares that with actual data to calibrate itself. And what they could integrate is to say that, postulate that the young forest has a higher transpiration rate, creates lower soil moisture and drainage, and lower stream flow overall. The old forest transpires less, creates higher soil moisture and drainage, and higher stream flow. Important for fish habitat, of course, in this case, but we'll see that has other implications as well. This model was applied now. Now, these models are really interesting because they can drive different scenarios. They are calibrated, and you can see when you change the forest in one scenario or another, you can learn by using models how a future precipitation range or climate scenario could play out in terms of hydrology. In this case, what they did was modeling watersheds with a different rotation age. They could show that, in particular, the summer minimum flows in the watersheds that had older forest growing, up to 100 years, was 2 to 5 times greater than the ones that were grown on a short rotation age. So basically confirming, the idea, or using the idea that the older trees transpire less water, and using that here on a watershed scale. That was a pretty cool result here. And indicating for us, older forests do have a greater benefit if your management objective is managing for water and streams. So the question now is, what do you do if you have a younger forest? And again, here the model was used, and the modelers used a watershed-wide approach here in the Tolt Watershed, which is in the Snoqualmie-Skykomish drainage north of Seattle, to look at a whole watershed effect. And they looked at the effect of a watershed that was managed with clearing, with even age regeneration and regrowth versus a thinned watershed. I just put that up here because that is a really characteristic stream flow curve for us in the Pacific Northwest. What you see here is this pretty jagged pattern of peak flows and runoff during the winter months, from January through December, but then this amazing curve that we see here during the summer months. That is our drying out of the soils, basically, or two, right? So soil moisture has a very similar curve with these spikes in there. Those are precipitation events that raise soil moisture as well. So for people who grow trees, knowing about this classic curve here until August, September, when the fall storms arrive again and water gets back in the streams, right? So what they did is basically look at the difference between a watershed that was thinned predominantly and one that was clear-cut and regrown densely. And this graph shows again the difference between the two. So on the vertical axis is the stream flow difference. The positive values here show times during which the runoff, the stream flow from the thinned watersheds was greater than from the cleared watersheds. And again, you see here, in particular during the month of August, September, October, when most of the water comes from base flows, below ground flows, the big difference in runoff patterns. Indicating to us that these thin stands have a great effect on summer stream flows where it might be most important for fish habitat in streams. Okay, to wrap this up, this is a graphic that I found that really nicely summarizes all of that. It shows at the bottom sort of three different cases: an open landscape, an intermediate landscape, and then a closed productive canopy cover on the right here. And it basically shows you that there are all these different processes that are involved in hydrology, right? From transpiration, interception, runoff, evaporation, infiltration, and groundwater recharge. They all react differently to these different amounts of cover. And that's the difficulty, really, that they all work in concert to create forest hydrology, right? And you can imagine that some increase, some decrease, but what we find overall is that when we look at groundwater recharge, there is, in fact, somewhere a happy medium where we anticipate that an intermediate forest cover does provide for the greatest groundwater recharge and greatest stream inflows as well. So that's hopefully the take-home message here. So real quick, I want to go through some ideas on peak flows, talking about hill slope effect, culvert sizing, and rain on snow events. I think this is very important because this speaks in some ways to forest management as well. How do we deal with greater or more frequent peak flow events in the winter when we expect greater differentiation between summer hydrology and winter hydrology? Here, peak flows. So first to plug, road engineers probably have the most difficult job. They have to disentangle two networks, one that goes down the hill, stream network, and then a transportation network that goes across the streams all the time in the name of transportation, of us getting there, right? And how to entangle these two networks is really difficult in some ways. We don't want to have roads washed out. We don't want streams to end at the roads. No, we create sort of culvert networks, bridges to funnel the streams through that network. But what we also do is we basically intercept the hill slope flow down the hill by creating roads and ditches. It's important to understand that we do this all over the forest. And then what we create is ditches that run along the road and ditch relief culverts that hopefully don't drain the sediment into the streams but onto the forest floor, right? It's an amazing task if you talk to road engineers how they do that and how often they have to do that and how much attention they pay to actually doing regulating flows. But what the trade-off is when we channelize those hill slope flows, we make the flows faster actually. So peak flow events actually increase. The water flows faster to the streams if we create these drainage networks. That's an important trade-off to understand when we talk about transportation, that we often increase peak flow events by having this whole drainage network on the landscape. So what do? We have culverts. Here on the left-hand side is a not so nice culvert, a perched, relatively small culvert. These are cases where we like to replace culverts because they create erosion, fish passage problems, and so forth. On the right-hand side is the culvert that was replaced. It was upsized because of the expectation of peak flow and better regulation. That is a common practice that we do, right? We size our culverts to peak flow events, probably 100-year events, and hopefully do that all over our forest landscape to minimize the effects of blowouts, culvert blowouts all over. But what we find when we look at climate models is that we actually expect greater peak flow events in the future. And when we did that with climate models over the next 40 to 80 years here, we find that by the middle of the century, we probably have to increase our culvert size by 20% across the board to capture the increased peak flow events on the landscape. And then by the end of the century, maybe by 30%. So those are figures where you can engage and say, okay, I have to replace a culvert. How do we do that? We can increase the sizes to capture the future peak flow events on the landscape. Just an idea for those of you that are dealing in road construction. Okay. Then briefly want to cover rain on snow events as well. I love snow. I go out in the snow all the time. I like to be up there in the zone where it's nice and white. There is a classic zone in our forest here in the Pacific Northwest that we call a transition zone, where we have rainfall and snow happening all the time. People around here say, if you don't ski in the rain, you don't ski much in the Pacific Northwest. Rain on snow events are those events that happen once in a while where we get a warm air mass. We used to call them Pineapple Express, now we call them atmospheric rivers. A warm air mass basically hitting the mountain ranges that have already snow on them, particularly in this rainfall transition zone there between the white line and the red line. And the more exposed snow you have in openings, the more you have synchronized melt-off, and sometimes tremendous amount of runoff. Oftentimes, I put a photo down here, the water coming down the hill is channeled within stream beds that are created by snow. And you have great sedimentation events coming off the hill in these rain on snow events. That is something that we try to prevent because of the increased sedimentation and the great peak runoff that we get during those rain on snow events. Typically, we like in this transition zone try to minimize canopy openings in the forest, maybe to 20-30% in a drainage. But the more we open up the forest, the more we get in terms of runoff from rain on snow events. I pulled this one out again here from one of Jessica's slides again. The peak that you see here on the right and the black on this graph is one that is created in a watershed that was snow dominated. Where we basically, during the winter, we get precipitation events. Some of that falls as snow and gets stored in the watershed. You can believe how important that is for somebody who manages domestic drinking water, because we get most of our demand during the summer months when we have the least precipitation. So storing some of the water as snow is really important, not just for drinking water, also for forest hydrology. So that melt pattern later in the season is really important, and we do expect it to decline over time. And I want to show you an example really quick here. So what we can do is we can look at freezing elevations during storms. I've done that here. On the vertical axis, you see elevation. My apology, that's in meters, and the writing is in feet. But we do see below a certain threshold, we see the system is rain dominated. You see that freezing elevations during storms can be all over the board, from 100 meters to 2,900 meters. Some storms are just warm, others are cold, right? And we can figure out at what point the system transfers from a rain-dominated system to a snow-dominated system. In our area, it is typically at 3,000 feet, and below that we have a transition zone, maybe of 1,500 feet, where we get rain and snow and mixed, and below that again we have a rain-dominated zone. Our expectation of future climate change is a 3-degree change, plus 3-degree change, we get a different pattern. So this is the future pattern of freezing elevations in our watershed based on climate change expectations. And you see that the peak of this distribution just moves up, right? Gets a little wider too. So freezing elevations are raised. So the snow zone that we get, where we are certain that we will have snow cover in the winter, moves up to 4,900 feet. We have very little land above 4,900 feet. So that gives us the idea that in the future, in the second half of the century, we have very little secure snow water storage and have to manage for that accordingly by different reservoir management. But also it speaks to us how much more the system will be rain-driven rather than snow-driven, how much less snow there will be from water, from snow melt during the spring and into the summer. Couple more graphs. I want to wrap this up, at least some of the data here, with just addressing the site or the terrain that you work in and its effect on hydrology, because there are different elements in a mountainous terrain, maybe in different landscape, that affect how trees grow based on how much water they get, how much exposure they have to temperature extremes, and so forth. And here are a few of the elements that we used in an analysis not too long ago. Snow cover is an important one. It can limit growing season, but also hydrology during the summer. Soil type is important because the size of the soil pores really speaks to the water holding capacity of the site. And then evapotranspiration just basically means southern slopes are being more exposed to drought or water demand on the trees. So overall topographic position up there on the right really has an effect on that whole hydrology of the site. And it's important to remember those individual things when you think about planting trees, where to plant them, and to plant the right trees at the right place. Was that the term?
For the right reason.
For the right reason. Okay, thank you. Okay. One thing to remember, water runs down the hill. That's pretty straightforward, right? We typically have better water supply at the bottom of the hill. Oftentimes we see trees growing faster and taller at the bottom of the hill, but also over time soil flows down the hill too. So soil depth is higher at the bottom of the hill. Keep that in mind when you plant your trees. There's typically better tree growth, better water availability at the bottom of the hill. And we use that in a model that is a GIS model that is available to categorize our landscape. And here you see what is called the Topographic Position Index. And that is a tool that can differentiate by looking at the landscape pattern. What is a ridge? What is an upper slope? What is a mid-slope? What is a valley? And what is a canyon? And along those same lines of water supply and different sites in the landscape, you can categorize your landscape here into the red ridge lines, shallow soil, exposed, low water holding capacity, and those sites in green and blue where you have higher water availability over the year. So planting accordingly can help you mitigate some of the effects of climate change and focus some of your management approaches to either valley bottoms or ridge tops. You can convert to other species maybe at ridge tops because they have a higher exposure to climate extremes, whereas you can maintain your ecological integrity or function in the valley bottoms where you have greater water supply into the future. Okay, I'll wrap it up with a couple of slides to sum it all up. Again here, as I showed, our state of knowledge tells us that the older forests do have a different hydrologic regulation than the younger forest, and if water supply is one of your objectives, that they do provide great benefits. The road drainage network plays a big role in peak flow management in the future as well. Keep that in mind. If we're talking about tree water status, regulating the forest density is probably a big player in most of the adaptation practices that we do, because the reduced sand density can lower transpiration and also, lower the competition for limited resources. And regenerating trees under the canopy or in canopy gaps can mitigate some of the evaporative demand and pressure on the small trees, maybe also eliminate some of the cold hardiness problems that somebody was talking about earlier. And then finally, a plug here again for snow. Working with canopy gaps rather than large forest openings minimizes the chance of large snow and rain events, but can also accumulate more snow overall than a forested area. And again here, a plug for mixed species forests to increase the resiliency of the system to changes in hydrology. It's very important if you want to regulate hydrology from a forested landscape to maintain that function into the future, having a mixed species forest that can adapt to future changes. And I'll leave it at that. Thank you very much.